Good morning, everyone. So we're switching gears a bit now, going more to the numerical methods, and it sort of goes along what Stefan earlier mentioned. Infinite computing resources, of course, we don't have them. So we need to make do with the computers we have. And in line with the name of this workshop, which is New Directions in Multiphase Flows, I want to show you a new direction in numerical multiphase flows. And then ask the question, is it worth it? So for those of you in the room who have tried to simulate a surface tension-driven flow using standard CFD method, you'll have come across a capillary time step constraint if you refine enough. That is simply coming from surface tension. So this has been work that has been going on over 10 years. I started this as a young, enthusiastic, and hopeful postdoc. Thought, how hard can it be? And it's actually quite hard to breach this capillary time step constraint. And I had some help from colleagues and postdocs working with me, Bernd van Wachem, Fabian Denner, and Romain Janaudet in trying to make this happen. And we had some funding from the EPSRC here in the UK and from the DFG in Germany. Okay, so as probably most of you are very well aware, there are certain waves that are surface tension driven on a gas-liquid interface, for instance, that are driven by surface tension, capillary waves. In these capillary waves, we know the dispersion relation based on their wavelength. For shorter waves, they will travel at a faster speed. And they're also very interesting in terms of, for instance, Rayleigh plateau instability, jet breakup, etc. So we see them everywhere where we have surface tension. The problem is that that poses a time step constraint for our simulations. And the first ones to hypothesize that and sort of formalize that were Brackbill and co-workers in their seminal paper in JCP in '92. They were not able to show that it exists. And the formulation they proposed is very good for practical purposes, although not exact. The practical issue with that is, so the traditional CFL condition, we refine our mesh by a factor 2, the time step goes down by a factor 2. For the capillary time step constraint, that's a bit more complicated. It's proportional to delta x to the power 3/2, which means at some point, if we go to higher and higher resolutions, which is typically what we want to do as we get bigger computers, this capillary time step constraint becomes the dominant time step constraint for our simulation. So the consensus in the community is we want to eliminate that time step constraint and breach it, so use larger time steps. So the objective is very simple. We want to have a numerical framework that allows us to breach this capillary time step constraint. So here, quick outline. So first, I will explain to you what this is, where it comes from. Then I'll show you two methods that we've developed to breach it. And at the end, we'll look at whether or not, and that's a question I cannot fully answer, that depends on the problem you have, is whether it's worth all the trouble you have to go through and the compromises you have to make. So the capillary time step constraint, for those of you who have had a reasonably good CFD course at some point, are familiar perhaps with the numerical domain of dependence, which was originally proposed by Courant and co-workers. And that basically means that the numerical domain of dependence must contain the domain of the dependence of the true solution, which leads to the very well-known CFL condition. So basically, our numerical solution should not move more than one grid cell in a given time step. So we can apply this to capillary waves, where C sigma is now the wave speed of the shortest unambiguously resolved capillary wave. And that is essentially a capillary wave with a wavelength of two times the mesh spacing. Everything that is smaller is not unambiguously resolved, so that's not relevant for us. This is basically the resolution limit. Not that what we resolve at that scale is physically accurate or an accurate prediction because it's under-resolved, but it still ruins our simulation. We can also look at this, and the experiments in the room might be more familiar with this, from the Nyquist-Shannon sampling theorem, which tells us that if we sample a band-limited signal, then we need to have twice the sampling frequency than the frequency of the signal we're sampling. So again, we can apply this to our capillary waves and say, okay, the frequency of our capillary wave is the phase velocity divided by their wavelength. So we know the wavelength, the minimum of the shortest capillary waves that we resolve, so the fastest one is 2 delta x. So then we can put this in our Nyquist-Shannon sampling theorem, and what we get is essentially the same formulation as the CFL condition. So we can look at this from a signal processing point of view, we can look at this from a classical numerical point of view and arrive at the same answer. So this should be relatively simple to put in practice. However, we don't have one wave, we might have several waves. So this poses another problem. They're superimposed, which means that the time between successive extrema might be reduced. So we have an effective worst case scenario, an effective wave number of these capillary waves that is twice higher. We can put this into our the formulation for our capillary, for the phase velocity. So we have another 2 here under our square root. Rho A and rho B, I should perhaps say, are the densities of the 2 fluids interacting with each other at the interface. And then we can propose a capillary time step constraint that now bears this delta x to the 3/2 relationship. So again, as we reduce our mesh spacing, we increase the resolution, we run into problems. Now, the problem that was initially overlooked was that, of course, like with every other wave that is in a flow, we have a Doppler shift. Those waves travel relative to the local flow. So we always have a worst case scenario where they travel with the flow with respect to our stationary mesh. So we need to take into account the tangential interfacial velocity as well locally. So this further reduces the maximum stable time step. So we've written all of this down on a piece of paper. Question was, how can we show that this actually is the right formulation, that it actually exists? Because in most cases, if you go above the capillary time step constraint, what you simply find is that there is no solution. Your simulation crashes, and that doesn't really show us that much, just that it doesn't work. So what we used for numerical validation, and I'll go a bit more into the numerics later on, it's a standard second order finite volume framework. In this case, we used an algebraic volume of fluid method. You could replace this with your favorite level set, or a diffuse interface method would do the same thing. And we use standard CSF model, which still is the state of the art today for surface tension modeling, where we have surface tension coefficient sigma, the curvature of the interface kappa, and essentially what represents a delta function at the interface, the gradient of our volume fraction, or as it's typically known with respect to VOF methods, the color function. And the interface curvature we evaluate with height functions in this case. So what we used, or what we found to be a very good test case for this, is a simple falling liquid film with a lot of the people here in the room are familiar with falling liquid films. So we perturb a gravity-driven falling liquid film on a substrate with an angle of 90 degrees, so it's vertically falling. And these falling liquid films, if you perturb them with a certain frequency, you get a shear-driven long-wave instability that leads to those solitary waves that you see here in the sketch. However, if the perturbation is shorter than a critical wavelength, then those perturbations should be attenuated physically. So that's very nice. So if we now perturb this with short wavelength and our waves grow, we know it's a numerical artifact, not physics. So that's exactly what we did, and we used 2 different time steps. So one taking the Doppler shift into account, one taking the Doppler shift not into account. And they're only 7% different, so they're not that far apart from each other. And the expectation was that, okay, the static constraint should not be sufficient because we don't take the Doppler shift into account, whereas the dynamic constraint should be sufficient. It's just below what the piece of paper told us. So those capillary waves should not grow. And that's exactly, thankfully, what we saw on the left with the static constraint, on the right with the dynamic constraint. You essentially, the flow goes from left to right, so does gravity. And we perturb this at the inlet, essentially, of our simulation domain. And we see that with the static constraint, those small perturbations on the interface, those small waves start growing very fast, and shortly after this time instance here, the simulation will have blown up. Whereas on the right, the same case, but now taking the dynamic capillary time step constraint, we see that those short waves, those capillary waves, are also excited, but they do not grow. They simply, at some point, leave our domain, and all is well. So we were able, that was in 2015 when we published this, so more than 20 years after the originally proposed by Bragg, we were actually able to show, okay, they were right from the beginning, although they couldn't show it at the time, and we can accurately quantify this. So the question is now, how can we make do with this time step constraint and accelerate our simulations? So the first thing we did is what every good engineer working in CFD does. We add dissipation. It's not elegant, but it works in many cases. And so to not just add randomly some dissipation, what we did is we took the velocity and did not take the Laplacian of the velocity, but we used the Laplace-Beltrami operator, so basically just the tangential dissipation at the interface, or the tangential Laplacian of the velocity with a surface viscosity. This can be chosen freely. We choose here a formulation that includes a Dirac delta function at the interface, and then we can get a formulation, for instance, as from the literature that was proposed by Heising, which has the dimensions of viscosity, and it includes surface tension and the time step in the numerator. So if the time step gets larger or surface tension coefficient gets larger, our interfacial viscosity, our artificial interfacial viscosity will increase, and the same happens proportional to inverse of the mesh spacing. So if we refine our mesh again, it will increase. So it has all the features that we need to counteract the capillary time step constraint. The way we tested this, or the test case I show you here, we've tested it with many different test cases, is the breakup of a semi-infinite jet by means of the Rayleigh plateau instability. So we excite this jet, and then it will break up. If we do this with a time step smaller than the capillary time step constraint, just for reference here, the colors show the velocity. If we go above the capillary time step constraint, our simulation is still stable, here with twice the capillary time step constraint, but we see clear differences at the time when surface tension becomes important. And that's perhaps not surprising. We're adding dissipation, so obviously that will change what we predict. So yes, we can reach the capillary time step constraint, but the quality of our results suffer. Here, this capillary jet is not a particularly favorable test case for this method, I should say. If I would show you results for a falling liquid film, you would see much smaller differences. So it depends hugely on the test case you have, how big that price you pay is in terms of accuracy. So we tried the more complex approach, and that's really doing everything implicit. So solving the entire system of equations that we have implicit the same way we can preach the traditional CFL condition. If we want or should do that, it's a different question. But we want to do that, the same principle applied to surface tension. So we developed a coupled implicit finite volume algorithm, again, second order accurate. And what we do there is that all governing equations are solved in a monolithic single system of linearized equations. And we have pressure, the three velocity components in 3D, and the color function, so the VUF volume fraction, as implicit solution variables. And then we followed 3 implementation principles. So we found 3 implementation principles that are key to making this work. First, each term of our governing equations, I'll present them to you in a moment, should make an implicit contribution to one or several of our solution variables. We need a consistent treatment of transient and advection terms. Okay, that should always be the case, ideally. And we need to treat surface tension implicit. And the difficulty there is that we have 2 variables, so basically the interface curvature, so the shape of the interface, and the gradient of our volume fraction, so essentially our numerical delta function that we need to treat implicitly here. So first, continuity equation, we retain the full continuity equation also for incompressible flows, because that allows us a consistent discretization of transient and advective terms. Okay, if we discretize this, and I want to point out here especially the green terms with the star, because those are the terms that we treat implicitly. So we do, essentially, we apply a Newton linearization of the density with respect to the volume fraction, where the volume fraction is taken into account implicitly. We have here the flux in the advective term. I'll tell you more about the flux in a moment, that we also treat implicitly. Looks fairly straightforward. We do the same thing with the momentum equation, which we also keep in conservative form. Gets a bit more messy because now we have to treat not only density, for instance, in the transient term, but also with, the velocity implicit. So again, we apply Newton linearization. We have, again, the same flux as in the continuity equation here in the advective term that we treat implicit. Pressure is treated implicit. All the velocities of the stress terms are treated implicit. And for the surface tension, the interface curvature as well as the color function or the volume fraction are treated implicitly. So there's a lot of implicitness here, a lot of terms we need to discretize correctly. Lastly, we need to advect our interface or our volume fraction field. Like I said, we use an algebraic VOF scheme. So typically we want to solve this transport equation. Problem is that we have this non-conservative advection term here that doesn't really fit in with our discretization. So we apply the product rule to have a conservative advection term and then basically a divergence correction, divergence of velocity. Of course, for an incompressible flow, this should be 0, but that's only true once our result in each time step has converged. So getting there, this term is not 0, and we need that simply for convergence. Again, we discretize that with the same idea. We have implicit fluxes and the implicit volume fraction here in the transient term. Now, how we discretize these fluxes is very important. First of all, because it needs to be consistent. Second of all, we have a collocated variable arrangement. So it's not the standard or the more accurate staggered arrangement, but we have a collocated arrangement. So we have pressure velocity decoupling if we don't do anything special. And typically how this is solved in CFD by simple methods, piezo methods, by the Colella-Glatt scheme that is used in Basilisk or Garris, for instance, or any other code, is by adding a low-pass filter on the pressure or the velocity field. So what we do here is we use a momentum-weighted interpolation, and we need to make sure that pressure and surface tension are well balanced. Otherwise, we get some spurious velocities. So we have this flux F, which is the product of, the phase area of our mesh phase, and the velocity perpendicular through this phase, which I call here the advecting velocity, which we treat implicitly. So that is, first of all, it contains basically just simply the velocity at the phase projected in the normal direction. But then we have this pressure term here where we take all these pressures again implicitly, and that's essentially a low-pass filter on the pressure. We need to balance that, so we need the same low-pass filter on our surface tension term, where we have the curvature, the volume fractions, everything implicit. And then we have some transient terms to make it consistent for small time steps, but that's not essential to this talk here. So this is a lot of work, took a lot of fine-tuning, how we essentially implement this. And so we end up with a very large system of equation. And I just show you here the submatrices that correspond to each equation with respect to each of our solution variables. None of them is zero. None of those, they're all sparse, but none of them is zero. And we end up, so each term of the governing equations makes an implicit contribution, and we end up with huge discretization stencils, often more than 100 neighbors, which comes mainly from the implicit height function method, which has typically a 3 by 3 by 9 stencil. And you have 6 neighbors that you include here, for instance, as well. So we end up with very large stencils, a lot of non-zeros. So basically inverting this is not a particularly nice exercise. Okay, so does it work? So a simple test case is a 2D standing wave that you see here. We have 2 fluids at the top and at the bottom and an interface separating them. We initialize that with a sinusoidal wave with a certain amplitude. And if this amplitude is small, then we have an analytical solution, and the kinematic viscosities of both fluids are equal. We have an analytical solution for how this wave is going to oscillate. And we did that with different resolutions, leaving everything else the same, and we can see that we can easily go to 50 or 52 times the capillary time step constraint just by increasing the resolution. We get the same result, stable result, so that's very nice. We have achieved essentially what we originally set out to do. Only took us 10 years to get there. Of course, not full time. Second case I want to briefly show you is the breakup of an infinitely long liquid filament by means of the Rayleigh plateau instability. So we perturb this cylindrical filament here. It will then evolve to break up. This is a nice case because we have linear stability analysis for comparison. Or we can also look at the singularity in finite time that is developed as this ligament breaks up. So first here we see the relative deformation with respect to the minimum radius as a function of the dimensionless time. And we see that at the beginning the solution follows the implicit theory of Rayleigh, then goes to the viscous theory of Weber, and at some point, it will break up. Again, I want to point out here 2 times and 8 times the capillary time step constraint we apply here. So time steps that are significantly larger than what we could have done, what we're able to do previously. We can look at the finite time singularity. Jens Eggers has pioneered this solution where essentially at the beginning, where tau here is the dimensionless time to break up. So at the beginning, the radius sort of follows a tau to the power 2/3 decay, then moves on to into a new regime dependent on the Ohnesorge number, and then below this dashed dotted line, we have essentially a resolution that is smaller than 1 cell. Will break up, but we can see that our solution again follows what we would expect from theory. Okay, so we can again breach capillary time step constraint. We have to pay for it by a very complex implementation. Okay, so that brings me to the last point: is it worth it? So yes, we can apply larger time steps. That's nice. Our solution accelerates typically, and that's more like a rule of thumb at this point. Typically about square root to the factor you increase your time step. So if we go to 10 times the capillary time step constraint compared to applying time step equal to capillary time step constraint, we can expect a speed up of 3 to 4. But we reach a new time step constraint, which is actually defined here by this polynomial, which includes the capillary time scale, the viscous time scale as well. And if I show you that for the capillary wave that I showed you a few slides ago, it will look like follows. So because we have here the viscous and the capillary time scales, we can form an Ohnesorge number based on, or Laplace number, based on this wavelength, so the shortest resolved wavelength. So the Ohnesorge number is here plotted on the x-axis. And we can see that basically in the inertially dominated regime, we can go above the capillary time step constraint, but only by a factor of 6 or 7. Whereas if we go to sufficiently viscous flows, we can easily go 1,000 times larger than the capillary time step constraint. The caveat with this is that those coefficients A1 and A2 are case dependent, and we haven't been able to find any sort of relationship that would allow us to predict this a priori. And that depends also, for instance, on the density ratio, on the viscosity ratio, on just simply on the geometry, let's say, of the case. But anyway, we reach sort of a new time step limit, which we believe has to do with the linearization of the equations, but that's still an open question. Now, we've developed this with an algebraic volume of fluid method. Like I said, you could interchangeably also use the level set method, for instance, or diffuse interface method. But in terms of accuracy, they're clearly inferior to geometric volume of fluid method. That is the state of the art today. If you think of PLIC, where you have linear reconstruction, now more and more we see attempts at doing parabolic reconstruction. So they are substantially more accurate. And of course, we can't expect to not resolve a phenomenon in time and predict it accurately. So, of course, we also pay in terms of accuracy. If you see here, for instance, as we go higher in time step for this capillary wave, we will simply not accurately predict the phase anymore, so the oscillation frequency. And I should say here, especially on the plot on the right, each of those dots are actually a discrete time step. So you see there are not that many in this oscillation, but of course then we can't predict the phenomenon correctly anymore, so we need to be careful how far we push this. And last but not least, we have to deal with a very tightly integrated numerical framework, which first of all is prone to systematic errors and bugs. Just simply from a practical point of implementing this, it's very difficult to do it bug-free, and even if you do it bug-free, you don't believe you've done it bug-free. And because it's so tightly integrated, it's also very complex to define unit tests, for instance. We can't simply take one piece out, test it, and see, okay, it works. We always have to test the entire thing. So debugging this is an absolute nightmare. And obviously, code maintenance and extension becomes a significant problem. Last but not least, hardware limitations. We have large memory consumption. So again, that's a rule of thumb. From my experience, 1 million mesh cells requires about 100 gigabyte of memory. So that's not only limiting in terms of the memory your computer needs, it's also simply a performance limitation that comes from the memory bandwidth at this point. Which CPU you have is not that important. It's how quickly it can access memory at this point. So there are problems which I'm sure will benefit from this type of method, but it should basically be a method that lives closer to the high Ohnesorge, in the high Ohnesorge regime. Clearly for low Ohnesorge number, I don't think you get enough benefit for the price in terms of implementation or hardware that you would have to invest. So in conclusion, okay, the capillary time step constraint originates from a CFL condition, and we can quantify this accurately, show that it exists. I've showed you briefly an artificial viscosity model. The beautiful thing about this is you can easily implement it in any CFD code. It doesn't take that much work. It adds dissipation. So that's obviously also sort of not an ideal thing. And lastly, we've developed a fully implicit numerical framework that does not add an artificial dissipation term. It's very resource intensive, both in terms of the hardware you're using and also the people who have to implement this. And with this, I'm at the end of my talk. I hope you enjoyed it, and I'm looking forward to your questions.
Thank you very much. We have extra time for questions because we did group photo yesterday. So we have 15 minutes, and the lunch will be served at 12:30. So not now. So we have time. Okay, first Christoph.
Thank you. I'm not sure I got why you need so many memory. Is it related to the implicit method or just?
It's purely related to the implicit method, and that we have an enormous number of neighbors, so many non-zeros. So it's not so much storing this matrix, it's still an extremely sparse matrix, but as we invert it, it becomes a dense matrix, and then really memory becomes the main issue. Also a bit the parallelization, but actually it works, it scales beautifully parallel even, so with a bit of extra work and thought about it, but it's really just as this matrix is inverted, that's where the memory bottleneck comes from. So maybe a matrix-free approach could be a solution to that.
Stefan, please.
Okay, thank you. Really fascinating talk. It's nice to see that at last works. Have you considered using energy-stable methods?
No, not yet. We really, at this point, we were interested in getting it to work with the method we have. Like I said, it would not be difficult to replace the method to a vector interface. That's not the challenge in all of this.
Thanks. So when you were showing the results plotted against Orner-Sorge number,
yes,
this was all for that.
That was for this one case over 4 orders of magnitude of viscosity.
Right.
Just to, I mean, at this point it was just basically pushing for each Orner-Sorge number, each case to the point where it broke, essentially where the simulation crashed, and those are.
Okay. So this is.
Sorry, I didn't say that. Those are the dots that we see here, and then we just fitted A1 and A2 to those points. So we can do this for every case. We did that as well for other cases, and this sort of formulation holds. The question is, what are the coefficients?
Well, I guess my question is simulation crash really the metric that you should be using? Do you believe the results up to the point at which you see the crash?
That's a good question. I would be careful. Again, I think it depends on the case you're having. In this capillary wave case, you see very quickly that the phase error becomes significant. It's a very case-dependent thing. That's why we don't really have a full answer yet.
Thanks. Any other questions? Yes. Yes, Mirko.
Sasha. Fabian, a super naive question, please forgive me. Could we iterate between solution of the volume fraction equation and momentum equation, like we solve one, we solve the other, we resolve the volume fraction with the updated velocity field, we solve again the momentum equation with the updated volume fraction field within the same time step?
No. The simple, and I explain you why, or I explain why I think it's no, because the first attempt we made, and I was, again, almost 10 years ago, is we took this implicit, I go back to, we took this implicit but not the curvature, for instance. And just by not taking the curvature we updated in each, like nonlinear iterations as we approached solution in the time step, we updated this, and it was still not enough for it to be stable. So if you would completely take out the color function or the volume fraction equation and just do it sort of in an iterative manner, it would not work. It doesn't even work if you take one of those two components out of it. So, or if you defer one of those two components. Unfortunately not. That would be beautiful.
Yeah, I can try.
Okay, thank you. Oh, yes.
Thank you for the nice talk. I was wondering if this fully implicit would improve spurious currents as well. I mean, in a sense that because iterative, when you do it, then curvature wouldn't be accurate. But for implicit, does that help?
No. In principle, it does not help. Actually, what helps is this artificial viscosity model. That helps quite a bit with spurious currents, probably more so than actually with the time step constraint. But simply because you have additional dissipation. The fully implicit, we didn't see any difference in spurious currents, to be honest. Of course, there's a tiny bit because your time step is larger, so they evolve slightly differently, but it doesn't solve the problem or make it worse, put it this way.
If I may, sorry, another one. It's in response to that comment about the partitioning, is that what are you using for your linear algebra?
At the moment, yes, that's an excellent question.
Because the reason why I ask is because you may find that a partition approach helps you in preconditioning, where you don't need to solve the system as exactly.
I think that's one of the weak points of our work. We haven't made any effort to make the linear algebra better. So what we use is Bloch-Jacobi preconditioner and a conjugate gradient solver. I think there is a lot to be gained if you were to tailor, especially the preconditioning, to just having this very nasty matrix with those very scattered non-zero values. I think that's already, could have huge potential. We're not smart enough. That maybe sounds a bit too negative, but it's not our expertise.
Okay. Okay. Another question from Jurko.
We can.
You have too much time for questions.
Well, we
Yeah,
can. We can fill this 15-minute
No
gap.
lunch yet.
I guess it's also related to the question Andrew just asked. I suppose the parallelization of the solution of that linear system becomes very messy also.
Yes, thankfully we didn't do that ourselves. The good people from PETSI have taken care of that. So we take the PETSI library for the linear algebra because, yeah. But so the scaling is really not the issue here. Surprisingly, it scales very well. So I guess that's a testimony to the quality of the implementation that PETSI provides with their solvers.
Okay, thank you.
Okay, so the presentation and the questions after the presentation showed me that numerical analysis can be as fundamental as this mathematical analysis with deriving estimates for the model and in certain functional spaces. So it's very deep indeed, and yeah, it's a good example. So I understand and appreciate difficulties with numerical analysis, everything. Okay, not only numerical analysis, mathematics, experiments should be done very carefully and with looking at all obstacles. Mainly they are well underwater, but we need to know them. This means experience. This means we are specialists in that field. Thank you very much. Thank you.